Okay, so welcome back, everybody. Hopefully, your spring break was decently enjoyable. Um, so before before break, we were just ending our discussion of Alexandrian mathematics. We were almost right at the end, uh, the sad, tragic end of where it had dwindled to basically a single member who I'm going to be talking about now. That is, this famed school of mathematics at Alexandria had basically one member left. And of course, I'm going to talk a little bit more about the fall of of all of the mathematical work that had been done. But as I've hopefully given you an idea already, uh, there wasn't, there's not one date you can say like, oh yeah, past this point, like that was it. That was all the math that was done in the ancient world, and it just ended, for some number of years. It wasn't really any one thing. It had been dwindling. After after like the first century BC, basically it had been dwindling in, we'll say, like density of mathematical accomplishments slowly. So by the time of Pappas, the last big named Alexandrian mathematician I'm going to talk about, it had basically dwindled down to nothing. He was basically all that was left of it, and after Pappas, there was only some minor mathematics being done until basically the torch was passed, and Europeans wouldn't again contribute in a big way until much, much later, until the Renaissance, basically. So anyway, before I get into that, the announcement for this lecture, I said, I've already posted your second homework. It's due this Friday, but if you need a few more days, that's not a big deal. So have a look at it. It's mostly to kind of, warm you up for the midterm that I'll be posting also later this week. I'll post it like Friday afternoon or something, and you'll have about a week to do it. So it will involve both essay style questions and some math questions similar to the homework. And so this is kind of a warm up for that. And so also to that end, I've been talking up this info dump that I've been planning for a while. That's essentially morphed into what is basically a nice, hopefully, well, not entirely streamlined, I won't say, because it's pretty long, but it's a nice kind of compilation slash study guide for all the stuff that we've talked about. That's going to include a bunch of links, many of which are just, for fun, not necessarily super important. It's just kind of included because it's stuff that I found when I was looking up some extra material. So anyway, so I will pass that along also sometime this week. So anyway, that's the immediate plan. Okay, so as I had said, Pappas is our last big name mathematician. Pappas is the last big name, so my distinction between big name mathematician and not so big name mathematician has to do with originality of the work. So all of the mathematicians that I had listed as minor contributors after Pappas primarily wrote commentaries or published editions of previous works. So I'll try to go through the specifics of what they did. But basically, they didn't really contribute any original mathematics. They basically added commentaries to already published things like Euclid's Elements or works of older Greek mathematicians. And so that's what makes them minor contributors versus a big name. So Pappas of Alexandria, this was he was active approximately around 320 AD. So as I mentioned prior, by the time of Pappas, the school of mathematics had one member, and it was him. So he was the last lone member of the school of mathematics in Alexandria. So he did a lot of work in geometry. By far his most famous contribution is Pappas's theorem, or the theorem of Pappas, or Pappas's hexagon theorem. So This is Pappas's theorem, or Pappas's hexagon theorem. I'll let you find the hexagon in this picture. So what is Pappas's theorem? Now I could write out the statement, and maybe I'll do that in words here in a second, but I think I would prefer to instead draw the picture first. So imagine we have two lines. Now there's a version of this theorem for lines that are parallel, but let's say that we have two lines like this that are not parallel. Okay. And on these two lines we pick triples of points. So maybe we pick points A, B, and C on the first line, and we pick points, say, A prime, B prime, and C prime, okay, on the other line. Okay. Then take our straight edge and we draw in connecting segments in the following way. So I draw in two connecting segments to A and B prime, A and C prime, to B and A prime, and B and C prime, and between C and A prime, and C and B prime. Okay. All right. So when I do that, I get intersection points. So there's an intersection point between this segment and the B and A prime segment. And then I have an intersection, so I have A and C prime. So then I need the C and A prime segment. There we go. And then lastly, I get this intersecting point between the B and C prime and C and B prime segments. What Pappas's hexagon theorem says is that these points, if I've drawn this, so you see that I stopped a little short on this point, and so it's not quite going to match up. The idea is that these 3 points are collinear. Okay, the 3 intersection points I get are actually collinear. They actually lie on the same line. Okay. So the intersection points in this diagram, not every intersection point obviously, but the ones I've selected here, the intersection points in this diagram are collinear. Oh, I guess I need another L here. That's what Pappas's theorem states. All right, so it's a little bit more clear to see it drawn out like that than written out entirely. But this is the idea here. Okay. All right. Now, why is it called Pappas's hexagon theorem? See if in this diagram, now that I've drawn this line on it, it might be a little bit more complicated to see, but see if you can find the hexagon sitting here in this diagram. But that's why it's called Pappas's hexagon theorem. Okay. So maybe I should identify these points. Let's call them P, Q, and R. So I have P, Q, and R. 3 points. So P is the point that is the intersection of the segment with AB prime intersected with BA prime. So that's my intersection symbol. Q is the point that is AC prime intersected with CA prime. And my point R is going to be BC prime intersected with CB prime. Okay, so these 3 points, P, Q, and R, are collinear. Okay, that's the statement of my theorem. Okay. Now, this might, just seem kind of like a neat fact, but why is this important? So Pappas actually probably didn't think it was that important. He just thought it was a neat observation. And of course, the proof of this was, so the proof, it can be proved in various ways. So this proof is really easy using linear algebra. There's a really, really quick way of proving this. But the original proof was through use of Menelaus's theorem. So we had mentioned Menelaus and his theorem previously. So this is via Menelaus's theorem. A few applications of Menelaus's theorem. And again, this can be proved pretty easily with linear algebra. But Pappas probably didn't think it was like super duper important, but it turns out to be a very important theorem, so much so that there are objects in geometry named after whether or not this theorem is true when you're talking about those objects. So these are known as Pappian versus non-Pappian planes. Okay, so there exist what are called non-Pappian planes. These are planes on which Pappas's theorem fails. Okay, but this is a very special thing because, as it turns out that Pappas's theorem is equivalent to multiplication being commutative. So that theorem, this geometric theorem that I wrote out here, right, that has kind of a complicated setup, this statement is actually equivalent to multiplication being commutative. What does that mean? It means that if I were to start out with the assumption that multiplication was, well, I don't know if it's commutative or not. Maybe it either is or it isn't, but I don't know. I could actually derive the commutativity of multiplication from Pappas's theorem if I assume that Pappas's theorem holds. Okay, and vice versa. If I assume that multiplication is commutative, I can derive Pappas's theorem. So this is pretty interesting, and this was used. So this is used by Hilbert, who we mentioned previously, as giving the modern mathematical treatment to Euclidean geometry. This was used by Hilbert in his treatment of Euclidean geometry. Okay. Even more so, it turns out that Pappas's theorem is extremely important in a type of geometry called projective geometry. Okay. Now, I don't have time right now to get into projective geometry, but I will later. Projective geometry is, the easiest way to think about it is the geometry of perspective. So actually, the first work in projective geometry, other than Pappas's theorem, which is, Pappas's theorem is sometimes taken to be the first theorem in projective geometry. So it's like the first projective geometric theorem. The first work in projective geometry was actually done by artists. It was done by Italian artists during the Renaissance, and it was in their work on perspective. And if you want to see the difference in Italian art, the early Italian artists in the 1400s versus, say, like artists from other European countries that were late to the party, if you want to see the difference between a flat, non-perspective drawing versus something drawn in perspective, I won't do it right now because I don't have them ready, but maybe next time I'll show different pictures of a completely flat picture versus something drawn in perspective. So work in art is actually what led to the very early understanding of some of the basics of projective geometry. But it turns out projective geometry is kind of like is kind of like the most primitive sort of geometry, but there's a niceness to it that that basically, in a sense, you can kind of view most sorts of geometry as being, or as living inside of projective geometry. So I won't talk about that more until later. Another main thing I could tell you is, you know how Euclidean geometry was all about compass and straight edge construction, so much so that we actually thought of, every single thing that shows up in Euclid's Elements can be constructed with compass and straight edge. In fact, that Euclidean geometry is basically the set of all things that can be constructed with compass and straight edge, together with this completeness axiom of Hilbert's, if you like. Okay. Projective geometry is like straight edge only. So it's like doing geometry with compass and straight edge, except you've lost your compass, so you only have a straight edge. And you might say, well, what could I even do if I only had a straight edge? I don't even have a compass, so I have no way of telling distance, right? Compass is the only way of computing distance in these constructions, so how do I even tell distance? Well, you don't in projective geometry. Not like that anyway. Okay. To see how that works, I would have to do a lot more. So I can actually refer you to some specific videos that I actually have uploaded on this same channel. But anyway, I'll do that later when we talk about projective geometry. So anyway, this is the main importance of Pappas' theorem. So it actually turns out to be a pretty far-reaching theorem. This wasn't realized by Pappas, of course, but he was the first to codify this. Okay, so for the minor mathematicians that I've already mentioned, so there's Hypatia. So she was the daughter of Theon of Alexandria. So she died in 415 AD. She was killed by a mob during anti-pagan riots. So there have been various theories about whether her death was directly linked to the Bishop of Alexandria at the time or not. There's no conclusive evidence. It's not much is really known why exactly she was killed. She just got unlucky. But she had written commentary on Ptolemy's Almagest, and she had also put out an edition of the Elements. So published an edition of Euclid's Elements. And why did I write that with lowercase? And wrote commentary on the Almagest. All right. So there's various things that have been named after. There was also there's a 19th century novel named Hypatia that was based on her story. There was Proclus, who I've mentioned previously, commented prolifically on the first book of Euclid, and he mostly, what is important about Proclus is he provided a lot of the some of the historical stories about the development of Greek mathematics came from Proclus. A lot of those facts that I was stating about Pythagoreans, for instance, early on, actually came from this commentary on the first book of Euclid. So he was known for commentary on the Elements. First book. Many stories concerning Greek mathematics. Or rather, the history of Greek mathematics. So a lot of those anecdotes, a lot of those stories about how, for instance, the story about Plato insisting on compass and straight edge constructions, I think Proclus was the first to actually ascribe that to Plato. Of course, this is hundreds of years after, so take that as you will. But actually, so Proclus was active. He lived from 410 to 485 AD. So 410 to 485 AD. There was two others I mentioned. So I mentioned Nicomachus. Nicomachus wrote a textbook on number theory that was kind of like a problem solution style book. So in this big tome that I have that contains Euclid, Archimedes, Apollonius, Hypatia. Nicomachus is kind of a strange name to include with these three. These three are like, high tier. Nicomachus is very much low tier in terms of what he actually contributed. The reason why he became popular was that his works survived into the Middle Ages and were kind of sort of used as textbooks in the Middle Ages. The problem is that they're vastly inferior to just Euclid's Elements. So they contained much less mathematics than just the Elements, for instance. So Nicomachus is another one of these small names. Boethius is another. So Boethius wrote a book while he was in prison in about 525 AD. That also he also wrote what was called it was arithmetic and geometry. So like Nicomachus, his book was also used as his books were also used as kind of textbooks during the Middle Ages, but again contained far less mathematics than the Elements. The biggest contribution that Nicomachus made was actually in giving a little bit of history of the Pythagoreans, because Nicomachus himself was a Pythagorean. Anyway, so those are the last contributors from the Alexandrian school. And so in 529 AD, Justinian closed the pagan schools of philosophy. So in 529 AD, Justinian closed the pagan schools of philosophy, which officially ended, Alexandrian mathematics. Now, of course, this, as I hope I've given the impression, this is not what did it. This is merely like the official bookend on a long process. So as you saw, right, Pappas was working in 320 AD. He was already really like the last member of the Alexandrian School of Mathematics, and basically nothing was done but preservation and commentary post Pappas. So for the last, say, 200 years of the existence of these schools, basically nothing was done. So it's not like, I don't want to give the impression that this event put the end on it. This is merely a formality, really. And so this is, if you like, you can use this as the beginning of the Dark Ages, but of course there's no one date that begins the Dark Ages, and a lot of historians would fight me for calling them the Dark Ages period, but we'll restrict our attention to mathematics. And so I'll ignore any technological innovations. I'll ignore any innovations in, in government type or anything like that. I will purely stick to mathematical achievements. And in terms of mathematical achievements, it's completely objective to say that it was a massive gap of a dark age where basically nothing was done. And so you might have heard a popular story. So a popular story is about the Library of Alexandria. So this is more. So what about the Library of Alexandria, right? The famous library, center of the world's knowledge, all of that. So there's an oft-repeated story that when the Arabs conquered Alexandria in 641, so Arabs conquered Alexandria in 641, and you may have heard various stories about the destruction of the library at the hands of the conquerors, but it's not actually probably what happened. So the library was probably already in pretty serious disrepair by this time, and there's a lot of primary sources that indicate that essentially, the library had basically never recovered for the last few hundred years of its existence from various damage that it had sustained, and also just falling into neglect and general disrepair. So the most often repeated story is that one of the commanding officers in the invasion demanded that it be destroyed because it contained, heretical books or whatever. But that story was likely actually, first of all, the earliest version of that story came many hundreds of years later, like 600 years later roughly, and it was probably a story that had been kind of bastardized and mixed around, actually describing the destruction of some other library that had taken place at an entirely different time. So there's a library supposedly destroyed by Saladin, for instance, and this story may have actually been referring to that library destruction rather than this one. So Arabs conquered Alexandria in 641, but the library was probably already all but destroyed. So it's not maybe that satisfying of an answer to kind of a big historical question, but that is how it goes sometimes. Okay. So what is true is that as far as European mathematics, globally there was a dark ages mathematically. So this is the dark ages of European mathematics. And they wouldn't begin to rouse themselves out of this until much, much later, many, many hundreds of years later. Okay. And so, since the European mathematicians take a break during this large stretch of time, it's a very good opportunity to shift focus and talk about mathematics in other places of the world, both during this time and what we know about the mathematics that occurred before. So in the case of these, unfortunately, not as much is known about the development of their math prior to Western contact, but some is known. So for instance, the first that we'll talk about concerns mathematics of China and India. Okay. All right. And so, the Chinese, the development of their mathematics, not that much is known about exactly how it was developed prior to 200 AD. So prior to roughly 200 AD, not much is known. One thing that is known is that there is a book that's titled Arithmetic in 9 Sections. So this was written sometime before 200 AD. If you know much about Chinese history, you'll know that round about this time, in the end of the end of the Han Dynasty, there was a lot of turmoil, and it can be a real headache trying to pour through exactly what was happening in China at these various times. So very, very tumultuous. I mean, all the way. Well, there's many stretches from this point on that were really tumultuous, all the way up through this time period we're going to be talking about. But anyway, so this Arithmetic in 9 Sections was written sometime before 200 AD. It is very similar to the Rhiine Papyrus in that it is like problems and solutions. So it's a problem list with solutions. So similar to Rhiine Papyrus. So what types of problems? They really liked these linear equations. So say, in linear equations and in unknowns. So they could do this for arbitrary n via a method that was basically equivalent to Gaussian elimination. I'm getting a message from YouTube saying that my stream may not be smooth due to some bandwidth issues. So please let me know if it starts cutting out or anything in the chat. If it starts getting blurry or cutting out, let me know, and I might have to restart the stream or something. But anyway. So in linear equations and in unknowns is the sorts of things they were interested in. So let's have 3 equations and 3 unknowns. So 3x plus 2y plus z is equal to 39. 2x plus 3y plus z is equal to 34. And x plus 2y plus 3z is equal to 26. This is literally a problem directly from this book. Okay, so 3 equations and 3 unknowns. To solve this, the method they use is basically equivalent to Gaussian elimination. Okay. Right, which is the typical method of, solving by isolating variable, then back substitution, right? This is one way of thinking about it. So this is basically how this was done. Why were they so interested in systems of linear equations? It's been suggested that one reason that they might have been interested in these kinds of systems is because this is linked to magic squares. So this is linked to magic squares. And they were very interested in this phenomenon. So what's a magic square? A magic square is a square of numbers such that all the rows and columns have the same sum and the 2 diagonals also have the same sum. So for instance, 4, 9, 2, 3, 5, 7, 8, 1, 6. So this is a particular magic square that the Chinese were interested in. Supposedly, this was brought to humankind on the back of a tortoise from the River Lo in the days of the Emperor Yu. So what is this magic square? Well, let's sum the rows. So 4 plus 9 plus 2, that's 13 plus 2, so that's 15. Okay, 3 plus 5 plus 7 is also 15. 8 plus 1 plus 9 is, 8 plus 1 plus 6 is also 15. If I go down the columns, I get 4 plus 3 plus 8, that's 15. 9 plus 5 plus 1, that's also 15. 2 plus 7 plus 6 is also 15. And then similarly, I have 4 plus 5 plus 6 is 15, and 2 plus 5 plus 8 is 15. So the 2 diagonals also sum to 15. All right, so sum of all columns, rows, diagonals are the same. So the sum of columns, rows, diagonals are the same. So these are the same sums. Okay. Okay. Now, depending on whether or not you have taken 406 here at UMD or how much you know about elementary number theory, there is a famous theorem that is named after Chinese mathematics, known as the Chinese remainder theorem. Now, I'm not actually going to state the theorem. I'm just going to show where the Chinese remainder theorem arose. So this has to do with modular arithmetic. So this has to do with modular arithmetic. Okay. Specifically, it has to do with systems of linear equations in modular arithmetic. And without having to go into a lot of definitions about modular arithmetic and talk about these equations, maybe I should just say that dealing with more complicated modular equations was something that wasn't done until much, much later. It wasn't done until basically the late 1700s, early 1800s is when, actually maybe more like mid 1800s now that I'm thinking about it, is when more complicated than linear things were dealt with in this fashion. So the Chinese remainder theorem kind of remains one of the, it was like pretty much all you could use until much more advanced machinery was developed much, much later. And so what's an example of a Chinese remainder problem? So here's the problem that led to the theorem that allows you to solve this. So divide by 3, remainder is 2. Divide by 5, remainder is 3. And divide by 7, remainder is 2. So then the question is, what is the number? So this is an example of what's called a Chinese remainder problem. Okay, so you have a number, you divide it by 3, the remainder is 2. Divide it by 5, the remainder is 3. And divide it by 7, the remainder is 2. So what's the number? Well, it turns out there's infinitely many numbers that satisfy this equation. And the solution to this, that is an understanding of what's now called the Chinese remainder theorem, was developed by Sun Tzu, not to be confused with the author of The Art of War. This is in 400 AD, so solved this problem. In his solution, he only gave a single answer, not the infinitely many possible solutions, but it was clear that he understood that his method, could basically yield any of those solutions. Okay. All right. Okay. So there's Su Chung Chi. These are like anglicizations of Chinese names, so pronunciation is going to be bad. So in about 475 AD, gave upper and lower bounds for pi, essentially using the Archimedes technique. His estimation was actually sharper. Gave an approximation, so upper and lower bounds for pi using Archimedes' method. Now, the assumption is not that he had actually read Archimedes or anything like that, but it's a method similar to what Archimedes used to approximate pi. All right. In 9 sections of mathematics, mathematician Chen Zhushao. So this was in 1247. Found a root of a quartic equation, x to the fourth minus 763,200 times x squared plus a very long number. I don't think I can even read that. I'm just going to write off the digits. So 406,425 60000. Yeah. So we found a solution to this equation, or root of that polynomial on the left-hand side, using what's called Horner's method. Now it's named after Horner, but Horner lived in the 1800s. So this is from the 1800s. So I don't think he had a time machine. He simply invented Horner's method before Horner was born. Okay, or at least discovered it first. So Horner's method was rediscovered by William Horner in 1819. So this is due to William Horner in 1819. So this predated it by quite a bit, by like 600 years. So there's also there's also knowledge of Pascal's triangle. This is also known by Indian mathematicians that we'll see. So Pascal's triangle was known to Chinese mathematicians. So specifically, this was done in 1303. So this was 1303, and the name of the textbook in question was Precious Mirror of the Four Elements. It's kind of a cool name for a textbook. Okay, and this was done by Zhu Shiji. So this was Zhu Shiji. Okay. So basically, this there's some more things I could get into specifically in terms of some number theory contributions, but those are kind of the big things that are well known. So specifically, the Chinese remainder theorem is something that when you're taking your first course on number theory, you will be introduced to Chinese remainder theorem almost immediately after learning modular arithmetic, because it's kind of one of the most things that you can use to solve some of those early modular arithmetic equations. Okay, so Indian mathematics. There were a lot of individual contributors. There's kind of a big four, though, that are kind of the most noteworthy contributors to Indian mathematics. So the big ones, there's Aryabhata the Elder. I'm getting the warning from YouTube again, so let me know if the stream quality deteriorates massively. So he was born in 476 AD. Brahmagupta. You may have heard of Brahmagupta before, so maybe I'll number them. So Brahmagupta did a lot of stuff that we'll talk about. So he was born in, well, I don't know if when he was born, but he was active around 628 AD. Mahavira, active around 850 AD, and Bhaskara, who was active 1114 to 1185 AD. Okay. So these are the big four that I'm going to talk about. So there were some earlier, there was earlier Indian mathematics. Some is pretty early. It's not quite known exactly when it was written, but sometime between 500 BC and 200 AD, there were some ancient Indian mathematic texts. So here's an example. So the earliest Indian math texts are what's called Sulva Sutras. So it's rules of the chord. They were written sometime between 500 BC and 200 AD. Okay. Oh, I'm off screen. So what did they contain? They contained basic geometry. The geometry mostly had to do with the construction of altars. And they also contained Pythagorean triples. Now, I believe one of the few Pythagorean triples that was mentioned here is that 12 squared plus 35 squared is equal to 37 squared. So this particular Pythagorean triple is mentioned, but it's presumed that they actually understood the rule for generating Pythagorean triples in general. Okay. All right. Of course, there is an even earlier example of mathematics showing up in kind of an unforeseen place. So about 800 BC, there was an Indian text that had to do with music. So this is the science of verse meters. So science of verse meters. What is this? Well, so if you are doing Vedic poetry, the syllables are considered either light or heavy. So in Vedic poetry, that's a comma, not an S. Okay. Well, if the syllable is light, what gets assigned to it is a 1. If the syllable is heavy, what gets assigned to it is a 0. Thus, each line of poetry is a line of binary. Right? It's a line of base 2. Okay, 1s and 0s. Okay, which can then be converted into decimal, right? Okay. Treating it as base 2. Right. So also in this same text, conversion in the other direction is discussed. Okay. Right. So the association of poetry to math comes in this strange way, using binary to encode, what type of syllables you're using in your poetry. Okay. All right, so I'm out of time here. I'll pick up on Wednesday with our discussion of Indian mathematics, and then we'll get into Islamic mathematics. And maybe I will finish that by next time, and then we will talk about basically the pre-Renaissance stuff and what exactly caused Europeans to kind of rouse themselves out of the Dark Ages. So anyway, that's where we'll pick up next time. So have a look at the homework 2 that I posted, and I'll post more announcements as the week goes on. So anyway, I will see you all on Wednesday.